Hey guys, so very often it's useful when we're showing what our circuit looks like to not actually draw out the battery and draw out what a resistor looks like, to use symbols. Unfortunately, these aren't completely universal, so you might see a couple different ones. The one we're going to use for a battery has one line longer than the other line. The line that's longer is always the positive side of the battery. You'll also see combinations of this where it's multiple cells. And this means the same thing if you see it in a circuit. Sometimes this is also called an EMF. And this stands for electromotive force. This is what Faraday called it. I don't like it because it's not a force. It doesn't have a unit of newtons. It has a unit of volts. But that's where the EMF comes from. Sometimes you'll see the battery described as the EMF. If you have a switch in your circuit, it's going to look like a door that is ajar. So a door that's open. So if you were looking like a top-down view of a room and the door was open, it would look like this. And then the idea would be that you would actually close it. All the circuits that we're going to build, are going to have switches in them. And it's an added layer of safety. Resistors are going to slow down the flow of current. Their purpose is to drop the voltage. And they are drawn as a squiggly line. So the idea is that since it slows the current, that it's going to take a good amount of time for it to go through the resistor. And in our purpose, the purpose is to drop the voltage. So a resistor dissipates energy, which is another word for waste. If you remember from the demonstrations I did with the hair dryer, if I open this up, my hair dryer has 3 different settings. But when I plug it into the wall, I'm always going to get 120 volts. And so what those settings will do is maybe on the high, I use all 120 volts. But on the medium, I only use 80. And on the low, I only use 40. And I'm making up these numbers. So a resistor, when I switch this from one to the other, is going to have that current going through a resistor. And that resistor, if I only want 80 and I have 120, is going to drop that 40 volts down to whatever voltage I need, because I'm getting 120 no matter what out of the plug. Our units are going to be ohms. This is a capital omega. I think of it as looking like cowboy legs. My lasso. It has a symbol of uppercase R or lowercase r, and there's going to be colors on them that tell us what their value is. The first 2 give us the first 2 numbers. The third one gives us a multiplier. And the fourth one's always a metal one, and that tells you what it's guaranteed to. So it's called its tolerance. So it could be plus or minus 5% or 10% or 20% of what it's supposed to be. I wanted to open up the window. And you don't need to, we'll go over how to measure it and those things, but you don't need to memorize what these colors are for any reason. You can have a variable resistor. And so this could be one where you can change the resistance. If you think about like a dimmer switch in your car or in your home. That'd be an example. A rheostat is another name for this, or a potentiometer. The resistance of a wire is going to be dependent on its dimensions, what it's made of, and how hot it is. So the length of it, the cross-sectional area, what it's made of, and what the temperature is. It turns out that as our temperature increases, our resistance increases, because you're making things go faster and faster, and it's going to be harder for those electrons to get through because they're going to be bumping into things more often. And so here's the resistivity at 20 degrees Celsius for all sorts of different things. We also have semiconductors. Semiconductors are not conductors until you apply a small amount of voltage across them, and then they become conductors. So we really won't get into that, but transistors are an important use of this. We also have things that are superconductors, and it turns out that if you drop a temperature low enough, and they've actually done this, they just did it weeks ago at room temperature, but they did it by varying the pressure, so they kind of cheated in it. But the idea is that if we cool something, the temperature of something is a representation of the kinetic energy of all the molecules. So you can imagine as you cool it, if the molecules themselves are moving less and less, it's going to be easier for an electron to get through. Well, certain things provide no resistance at all at low temperatures, and these are known as superconductors. So anything below the critical temperature, they'll provide no resistance. And so we've had currents going for years in superconductors, and they've been undiminished. And so again, we know that the lowest temperature is 0 Kelvin, and that would mean that our molecules are not moving at all, which up to now has been impossible for us to get to. But we've had ones as low as 160 Kelvin that were found. So 0 Kelvin means it's not moving at all. If you want to know like the internal energy of an atom or a molecule, our potential energy is going to be the sum of the individual kinetic energies, and the sum of the individual kinetic energies is related to 3/2 nRT. And you might recognize the nRT from chemistry, right? So N's a number of moles, R is our ideal gas constant, and T is going to be our temperature in Kelvin. All right, so Ohm's law deals with our relationship in these ideal conductors. So like I said, this doesn't apply like the second law does to everything. It's only going to be for ideal conductors. What are ideal conductors? Things we plug into circuits are going to be ideal conductors, so our resistors. So V equals IR is the equation that is derived from this. It is not that. So if it's an ideal conductor, it will show this direct proportionality. If it shows something like this, it is known as being non-ohmic. So really, even though very often we take a light bulb to be an ideal resistor, it really isn't, because they heat up pretty regularly and they become non-ohmic. All right, a 3 ohm resistor is attached in series to a 24 volt power supply. Calculate the current and the voltage across the resistor. So I have a battery. It's going from positive to negative. So it's going that way. My relationship from Ohm's law is that V is equal to IR. So my current is going to be my voltage divided by my resistance. So this is 24 volts divided by 3 ohms or 8 amperes. And then I also know from the definition of current that I is equal to Q over T. So Q is going to be equal to the current, which was 8 amperes times the time, which is 30 seconds. And so I'm getting 240 coulombs going through. And this is the main equation in all of simple circuits and DC circuits, is this equation derived from Ohm's law, which is not Ohm's law. All right, so to review, voltage has a symbol of capital V and units of capital V, which are volts from Alessandro Volta. What is it? It is our electric pressure. So it tells us how much or how hard we can push these charges. What is the equation? V equals IR. Current can be a capital I or a lowercase I. Its units are a capital A. These are amperes and not amps. This is named for Rene Ampere. What is it? It is the flow of charge. If we say that it's the flow of positive charge, it's conventional current. And our formula is Q over T. Resistance can be a capital R or a lowercase r. The units are ohms, which is a capital omega. This is named for George Ohm. And this formula is not that important to us, but it's the resistivity times the length divided by the area would get it. What is resistance? Resistance drops the voltage and slows the current. So it dissipates energy. So as far as we're concerned, a battery is going to give us a constant voltage. So if something is changing in our circuit, it's going to be the current. Resistance is going to be the property of whatever the device is. Current has a direction, but it's not a vector. It has a direction because, like always, when you're trying to explain something, it's easy to relate it to something that you already know. And so we got this water analogy. And so like a river flows, they say that current flows. But current is not a vector. So it's the one thing that has direction that's not a vector that we're going to cover. Current and charge do not get used up. So whatever current comes out of the battery on one side is going into the battery on the other. What is used up is the actual metal, the chemical reaction that's causing the difference in potential. So over time, and that's why you have to replace batteries, the metal is being used up. And typically when you do, if it's a 1.5 volt battery, it'll stop being useful to you when it's like 1.3. So it still has potential. It just doesn't have enough potential to do what you're asking it to do. Circuits can have many pads and many resistors. The other thing we're going to do with this is looking at how to combine resistors. When you combine resistors, you can write that as R tot for total resistance or Req for the equivalent resistance. So this is going to be the resistor that can do the same thing as those resistors, take the place of it. If you have them in series, and series means one after another, you just add the resistors. A good example of this is when you have lights, Christmas lights, and one burns out, and the Eolic kind ones, and then all of them were also burnt out. So here's an example. We have two in series with each other, a 500 ohm and a 450 ohm. And what I'm saying is I could have one resistor that was the addition of these two, which is 950, and my circuit would be unchanged. All right, so in this case, I have a battery. You can see they drew the battery as multi-cells, unlike the way I drew it for you guys. One is 10,000 and one is 1,000. What would the total be? I'm just going to add these two numbers together. And so what I'm saying is that a 10,000 ohm resistor and a 1,000 ohm resistor could be replaced by an 11,000 ohm resistor and nothing would be different. There would be no difference in how the circuit acted. If you have multiple pads, that's going to make the resistance go down. And in this case, 1 over R total equals 1 over R1 plus 1 over R2. You're going to know you have this when you can take one of them out and still have a closed circuit. So here I have one that's 100 and one that's 50. So I'm saying that 1 over R total is 1 over R1 plus 1 over R2. You can rewrite this as 1 over R1 plus 1 over R2. So I'm going to have 1 over 100 ohms plus 1 over 50 ohms. When you combine resistors like this, when you combine resistors in parallel, it's always less than the least resistor. So I should get something less than 50, which I'm going to get 33.3. In your calculator, it'd be 1 divided by parentheses, 1 divided by 100 plus 1 divided by 50. Close parentheses, enter, and I get 33 1/3. So the idea is I could put 33 1/3 ohm in this circuit, and it would be the same circuit. All right. Here's another one where they're in parallel, right? So some could go this way, some could go that way. So it's 1 over 200 ohms plus 1 over 100 ohms. This one's going to be less than the least. I'd expect it to be less than 100. It's actually 66.6. So again, 1 divided by parentheses, 1 divided by 200 plus 1 divided by 100, close parentheses, enter. Now you get 66.6, which would be close to 67. And again, none of our resistors are going to be exactly what they are, right? That's that last stripe that they paint on there is the metal one. It tells you how close it is, what the tolerance one is. So you can do both of the things together. So sometimes you'll have resistors both in series and in parallel. All of these are 50 ohms. The first thing I'm going to do is combine these two into one. So we try to make it into one path. The combination of R2 and R1, I would call R12. And I would say that R12 would be equal to 1 divided by 1 over R1 plus 1 over R2. When you have two resistors that are the same resistance, when you put them in parallel, the total resistance is 1/2. So both of these are 50. When I put this in my calculator, I'm going to get that this is 25 ohms. So now I could redraw this as R12 and R3, and now I know that R12 is 25. And then to get the total, I would just take 25 plus 50, which would be 75. So I would say R total or REQ would be R3 plus R12. So that's just 50 plus 25, and I don't even need a calculator to add those two numbers. So my new total is 75. All right, if all of these are 10 ohms, what is the combination? Well, I've done this enough that I know that it's 13.4, but I'll go through it with you guys. So the first thing is I'm going to combine any easy ones. R2 and R3 and R4 and R5 share a path. These are each 10, so that means that 10 plus 10 is 20 and 10 plus 10 is 20. So I could put in 20 ohms for those. So I'm going to redraw this because I'm just adding those. So now I have R1 and I have R23. I have R6 and I have R45. And we're saying that these are 20. So if I had two 10 ohm resistors in series, I could replace them with 120 ohm. All right, so now I have a 10 and a 20 in parallel twice. So the combination of R1 and R23, which I would call R123, is going to be 1 over R1 plus 1 over R23. So this is going to be 1 over 10 plus 1 over 20. Putting this in my calculator, I'm going to get 6.7. I would get the same thing over here. So if I redraw this again, now I have my voltage. I have R123, which is 6.7. And I have R456, which is also 6.7. The total of these two, which I can call REQ or R total or R123456, would just be 6.7 plus 6.7, which would be 13.4. So what does this tell me? That if I had one 13.4 ohm resistor, it would replace all 6 of them and keep the circuit essentially the same. All right, so little review. Series, what does it mean? That they're one after another and that they share a path. How do I add them in series? You just add them. Parallel, it means that the current splits. It means you have multiple paths. The equation it's easier to write it like this than to do 1 over RP because you're going to have to get it in this form anyways, right? You don't care what 1 over RP is, you care what R is. The subscript S would be for series, the subscript P would be for parallel. Equivalent resistance is going to be the total resistance. So it's the equal resistance you could put in the path that would do the same thing. All right. Try this one without me and see if you can solve it. I got 4.8. And again, just in parts. First things I can combine are these two because they share a path. Then I'm going to find out what this is in resistance in parallel, and then what the combination of that is in parallel with that. And then I'm going to add that to this one to that one, and then the final two that I have are in parallel. I'm going to do one over again. All of these, I'll give you guys a chance to try to figure out what this is. 25. So 2 10s in parallel. If you have two of the same resistor in parallel, you just cut it in half, so it's 5. And I have a 5 and a 5 in series, which is 10. Then I have another 10 and 10 in parallel, which is 5. And then I have a 10, a 5, and a 10 in series, which is 25.